Hello, everybody. It is my pleasure today to welcome Nadeen Gebara. Nadeen is a final year computer science PhD student at Imperial College London. Our research focuses on accelerating data center applications with programmable in-network logic. And today she will be discussing with us, or she will be providing us a presentation on in-network aggregation for shared machine learning clusters. So without further ado, I will hand over the stage to you, Nadine.
Thanks. Okay. Hi, everyone. I'm excited to be here today and share with you our work on a network aggregation for shared machine learning clusters, which was recently published in MLSys. And just a bit about us. So I'm Nadeen, as I was just introduced, and I'm a student at Imperial College London. And this work was done under the supervision of Paulo Costa, who is a principal researcher at Microsoft Research, and in collaboration with Professor Manya Gobadi, who is an assistant professor at MIT CSAIL. So let's get started with the talk. So as you might have experienced, machine learning is a computationally demanding task. And over the past decade, the computational requirements for ML training has roughly increased by a factor of 100x over 2 years. However, if you compare this with Moore's law, you'd notice that there is a wide gap in what a single machine can support compared to the computational requirement of machine learning tasks. So the way to go about this challenge has been to utilize distributed training, where instead of only using a single machine or compute node to perform the training task, multiple computational nodes are used in parallel. And the idea is by using more machines, you can meet the computation requirements of ML training. And there are two main techniques to do distributed machine learning training. So one approach is the data parallel approach, where the model is replicated across multiple machines, and each of these machines then computes on a local set of the training data set. And these machines synchronize with each other periodically. And the other approach is to actually distribute the model on multiple machines, for example, on a layer by layer basis. And then each layer would take in its inputs, compute the outputs of that layer, and then it would get sent to another machine, which is in charge of handling another layer of the model. And of course, you can combine these two approaches in a more hybrid way. So in the talk today, I'll be specifically targeting the data parallel machine learning technique, since it presents more opportunity for acceleration by leveraging computation within the network itself. So let's take a deeper look at how data parallel training works and what exactly I mean by leveraging a network computation for data parallel training. So imagine the scenario where you have multiple compute nodes, which I refer to as workers here, and they are connected in a network using a network switch. So in the data parallel training, the model is initially replicated and initialized at the same state on each of these workers. And then the data set gets partitioned across these worker nodes, where each one of these workers computes the gradient using the subset of the data set. And after computing this gradient on each of these machines, the workers must then exchange the computed values with each other, combine these values and determine the average. And then the average is sent back to all the workers, who then use this average to perform the model update, thereby ensuring that all of the workers are always synchronized in terms of the model. So the optimal way, or the state-of-the-art way to do this averaging of the gradients today, is known as ring or reduce, where each one of these workers, after computing their local gradients, send a subset of their local gradients to only one other worker in this diagram. And you can think of it as having the workers combined in a logical ring topology, where each machine can only communicate with the other machine in the ring. So for example, as you see here, the green gradients start at worker 1, then they are sent to worker 2. Worker 2 now combines them into a partial sum, and then worker 2 forwards them onto worker 3. And now, as you can see, each one of these workers has the complete gradients of each of the partition. And after doing this complete computation, another round is needed to exchange the results back to all the workers. So as you might have noticed, this is optimal in terms of bandwidth, since each link is only used for one connection. However, it's not optimal in terms of latency, since you need multiple iterations to send the gradients to all the workers, and then you need another round to send the computed sums back to all the workers to do the averaging and update the model. So the main question that you can think of is, why not have all the workers send the values to the switch, and then the switch would compute the aggregation. And this actually has been shown, as you can see here, to reduce the number of iterations needed, where it only takes the worker to send their values to the switch, and then the switch will directly send back the results to all the workers. And this has actually been shown in many recent other academic works as well, to reduce the time it takes to aggregate the gradients. However, it's worth noting that most of these academic work target only small-scale environments, and there are still many challenges for the wide adoption of in-network aggregation in practical settings. So when you think of distributed training, you think of doing it in cloud services like AWS or Google Cloud or Azure. And in such cloud services, servers are usually organized in a topology. So one of the common topologies is a fat tree, where you have multiple layers that connect the servers using switches. And when you look at the switches specifically in these data centers, these switches operate at very high rates, approximately 50 gigabits per second today for a single port, and it's scaling rapidly to 100 and 400 gigabits per second. And these switches also have a very large number of ports. So essentially, that means you need to support line rate aggregation. And on top of that, you're thinking of a shared cluster. So you're not considering only aggregating the gradients of a single machine learning job, you're also keeping track of the gradients to be aggregated for multiple machine learning jobs, which is a challenging task. So the second major challenge is essentially that so far we've been thinking of this whole picture where you only have machine learning and network aggregation jobs, where all of these jobs actually want to use a network aggregation. However, not all tasks that are launched in the data center are necessarily machine learning jobs, or perhaps they do not necessarily rely on a network aggregation. For example, if you consider k-means clustering or other things like inference, where you don't need to do aggregation. And these two flows actually have quite distinct properties. So if you look at the non-aggregation flows, they're usually relying on doing no operations in the network, and one source sends a message to another receiver. And these flows usually have known mechanisms to ensure that there is no congestion in the network, and to further ensure that the bandwidth of the network is utilized fairly and efficiently. However, when you consider network aggregation, this is not the case. And at the moment, there are no efficient ways to ensure that this network is fairly utilized by both aggregation and non-aggregation flows, which is quite challenging due to the properties of aggregation flows. So in our work, we aim to address these challenges by presenting three main components, which are a bump-in-the-wire accelerator for line rate aggregation, which is able to support a network aggregation of multiple jobs at very high line rates. And we further introduce a congestion control protocol and a load balancing is used fairly and efficiently by both aggregation and non-aggregation flows. So let's start by looking at the accelerator. So if you think of the PANAMA switch, which is our programmable architecture for a network aggregation, the PANAMA switch or P switch has two main components. So the top part is it could be any commodity switch, and it performs the task of routing and switching. Whereas on the bottom is our main contribution, which is including an accelerator to perform this network aggregation task. And the key thing about this accelerator is that it's specialized to perform a network aggregation at very high rate. And on top of that, it also supports floating point computation, which is a feature that is not currently supported in the commercially available programmable switches. And therefore, we guarantee that we do not degrade accuracy by performing a network aggregation. So let's take a deeper look at how this aggregation accelerator works. So in this figure, we're going to start by first describing what happens when non-aggregation flows arrive at our accelerator, which are essentially the flows that do not require any aggregation. So once they arrive, they're first encountered at the parser. And the parser looks at a specific field, which usually indicates whether or not this packet is an in-network aggregation packet. And upon determining it's a non-aggregation packet, the packet is forwarded immediately to the output port, and then the switch deals with it like any regular packet. In the case of aggregation packets, the header parser sends these packets to dedicated buffers, and then the controller keeps track of whether or not all the packets that are required for a specific job have arrived at the ports. So once they are determined to have arrived, they are streamed into an adder tree, and effectively we support high rate by having many parallel adder trees that operate in parallel. And after determining the aggregation result, the packet is then forwarded through the output port to the switch for routing. So to evaluate our design and see whether it would actually meet the line rate, we prototyped it on here, as you can see. So we prototyped it on a net FPGA board, which is where we implemented the accelerator. And we use the Arista switch as our commodity switch. And we connected the net FPGA board to the Arista switch. And then we connected 4 servers to this net FPGA board. And what we did was we generated values, and from ML training, we encapsulated them in a specific packet format, sent them to the accelerator, and then verified that we indeed received the aggregation value of these gradients. And further, to ensure that we were able to maintain line rate performance, we ran an experiment where first we measured the throughput that was supported when we connected 2 of these servers directly through the switch and had them send packets to each other. And as you can see, the baseline for the 10 gigabits per second ideal link was roughly around 9.4 gigabits per second when only going through the switch. Then we sent packets through the net FPGA board. However, these were the non-aggregation flows that did not go to the dedicated logic for the aggregation. And as you can see, it also maintained the same line rate. And finally, we sent aggregation packets. So on average, the same line rate was maintained. However, you might notice it's a bit noisier, and that was because we had to use UDP as opposed to TCP because we were changing basically the packet within the network itself. Hence the need to provide our protocol, which I will describe later. And now we'll get into the protocol, which is the second contribution of our work. So maybe the first question is, why does in-network aggregation need a congestion control protocol? If you look at how usually things happen in a shared setting, you have different servers sending packets to each other. In this case, consider this green being the non-aggregation flow, which can use a congestion control protocol like TCP or any other TCP-friendly protocol, whereas the blue part is network aggregation job, congestion control protocol. So once packets are sent, this link that is shared by both of these jobs is going to experience some congestion. However, in the case of this job that uses a congestion control mechanism, this congestion is going to be detected by feedback from the network. And based on this feedback, this job is going to send packets at a slower rate. However, this job is oblivious to the contention and will keep on sending packets at a higher rate. And as this job maintains the same rate while this job keeps on slowing down, ultimately, the entire link bandwidth is going to go to the ML job, and this flow is going to be starved. Meaning that we need a way to make sure that starvation does not happen, and this link is shared fairly between both flows. So maybe the next logical question is, but why don't we just use TCP similarly to the way we do it for the other flows? So the thing about TCP and TCP-like congestion control protocols is that they are usually point-to-point. So you have a source that's sending a packet to the destination, then the destination sends feedback to the source to notify it about the state of congestion in the network, and then the source reacts with its feedback. Now, let's take a look at the idea of a network aggregation. You have multiple sources that are sending packet to multiple switches, which alter the content of this packet, and then the packet would need to send feedback to the source. Then you have another hop where the switch is going to send the partial aggregation result back to another switch, and similarly, this will repeat until feedback is provided on a hop-to-hop basis. Ultimately, what this means is not only do the destination nodes need to implement the congestion control protocol, but this must also be done on all the switches on a hop-by-hop basis, which would require complex switch logic and be quite expensive. So our proposal was to actually leverage the property of a network aggregation, where essentially, if you look at it, all the workers are going to send their packets, and all the workers would expect to receive a result which contains the aggregation of the partial results. So based on that, what we do is our accelerator always maintains the state of congestion and the state of the accelerator itself within the result packet. And then this gets forwarded onto the network and is further updated with the state of congestion. And this actually repeats at every switch until the result packet is sent back to all the servers. And then the servers would react to the state of congestion in the network, which is now included as part of the result packet itself through implicit feedback, instead of sending an explicit feedback for each link on its own. And this ultimately ensures that the link is shared in a fair way by both aggregation and non-aggregation flows. And the third mechanism we introduce in our work is a load balancing mechanism to make sure that the network is utilized optimally by both flows. So why do we need this? In the case of non-aggregation flows, there are usually multiple paths between senders and receivers, and there is a routing protocol known as equal cost multipath, which randomly chooses one of those paths. For example, in this case, it chooses this. At other times, it might choose this black path. And this ensures that the traffic that is sent by workers or the packet is uniformly distributed across the network and minimizes congestion or contention in the network. However, when you look at the task of a network aggregation, you usually want to find a common switch, which represents the minimum spanning tree, such that all the workers can send their aggregation results there, perform the aggregation at this common root node of the aggregation tree, and then the result is sent back to all the workers. And if you notice here, there's only a single and unique path from each of these workers to the switch. Ultimately, if you consider a very large model, let's say a 400 megabyte model that you want to perform a network aggregation on, then ultimately you're sending 400 megabytes of data through fixed paths to the switch. And as a result, you will end up creating imbalance in the network. So what we propose instead is to leverage multiple aggregation trees in parallel, such that each aggregation tree now has a subset of the gradients to aggregate, and ultimately the load is shared fairly across all links in a balanced way. And this actually shows benefits not only to the aggregation job, because now it can receive multiple results in parallel, but also to the non-aggregation job, because as you note here, the contention is reduced on this shared link. So once you put these three components of PANAMA together, what you ultimately observe is that PANAMA reduces the time to accuracy of data parallel training jobs in large-scale shared clusters. And the even more interesting result of our work, which wasn't very obvious at the start since we were focusing on the machine learning job itself, was that by reducing this load on the network and making sure the network is shared efficiently by aggregation and non-aggregation flows, many non-aggregation short flows were able to observe a very high improvement in terms of their latency or flow completion time. And we were able to observe this by performing large-scale simulations. So in terms of the large-scale simulations, what we did was we generated a set of ML jobs to represent aggregation flows and a set of other flows to represent non-aggregation flows. For the aggregation flows, we modeled these 6 models here. And to do that, we actually relied on values that were provided by the TensorFlow benchmark. While for the non-aggregation flows, what we did was we used certain data center traffic patterns to generate different flow distributions of varying flow sizes. And we considered 2 subcategories, which were the short flows and the long flows, since the key performance indicator of short flows is usually the latency or the flow completion time. So we focus on that for the short flows. Whereas for the long flows, what ultimately mattered was the throughput. And we compared in network aggregation to using the state-of-the-art ring or reduce method in order to perform this training task. As for the network itself, we simulated a fat tree topology with a total of 1,024 servers. So in terms of the result, we're going to start with the impact of a network aggregation on the normalized ML training time. And the way we measured this was we started increasing the traffic that was generated by non-aggregation flows. So consider first a cluster that is only running ML jobs, right? And they are all in network aggregations. And then consider introducing little by little more and more non-aggregation flows such that we increase the load on the network. And then we measured the mean training time of these models. So this was the result we obtained when using the state-of-the-art ring or reduce method. And it's worth noting that the time here is normalized against the perfect case where it was only in network aggregation flows and there were no other traffic in the network itself. And then once we performed a network aggregation, we observed up to 1.34x improvement in the ML training time. And as you can see here, this is not necessarily twice as much, which is what you would expect, since ultimately what a network aggregation does is it reduces the communication time. However, the models spend still some time on computation. However, when you look at the short flows, or let's say in this case, the non-aggregation flows, we did the reverse. So we have a dedicated cluster that is only running non-aggregation flows. And this was the ideal 99th percentile flow completion time in this perfect scenario. And then we started slowly introducing more and more ML jobs at a higher rate to the network. And the higher the rate at which we introduced these ML jobs, the higher was the load we were putting on the network. So if we start with state-of-the-art ring or reduce, and then what we do is we consider a slightly modified version of our work, which was introduced in previous work for a single rack setting, which did not have any congestion control or load balancing. However, what we did was we included the load balancing part, and we didn't include the congestion control part to see the impact of the load balancing and a network aggregation on performance. And as you can see here, the performance was improved by 2.25x. And then what we did was we further included our proposed congestion control protocol, which is our work here, which is PANAMA. And we could see also 2x more improvement in terms of the latency of the short flows when you compare it to the state-of-the-art ring or reduce. As for the throughput, we did the similar thing and we considered the throughput of long flows. So as you can see, ring or reduce's throughput is much lower than that of our work, as well as the prior work, which we augmented with load balancing, since the congestion control ultimately mitigates the latency from the perspective that the short flows are not starved as much and the throughput is sustained regardless of the approach taken. But ultimately, it's still significantly better than when you use ring or reduce compared to using a network aggregation. So in summary, PANAMA constitutes of three main parts that work together with the hope of actually making a network aggregation more applicable in practical scenarios and not only in limited scenarios where you have a very small number of switches or ML training jobs that are usually running in local settings. Thank you, and I look forward to taking your questions.
Oh, thank you so much, Nadeen. That's actually very interesting.
Thank you.
Interesting work. There is no questions currently here, but I do have a few questions actually to ask. So I can see that most of the algorithms or the models that you've been using to kind of like do a benchmark, they are like vision-based models that use convolutional neural networks that we know are they are very parallelizable or easily parallelizable. But however, I've tried using like recurrent neural networks or LSTMs or GRUs to see if they have the same performance improvement as you see in like the Inception vision models or the ResNet models.
Yeah, so should I keep on sharing, by the way, or it's...
Yeah, you can continue sharing.
Okay. So ultimately, the idea is whenever you are using, so I know in LSEs as well, whenever you are doing some sort of regression, right, you need to compute the gradients of these models.
Correct.
And this task, often you can do it on each subset of the data. So if you think of mini batch training, right, what you do is you're saying, instead of operating on the entire data set on once, I'm going to operate on each mini batch and do that multiple times. So the idea is now you're extending that to something which is data parallel training, where you're saying now each mini batch is on a different machine, and I can do them separately, and at some point I need to average them. So ultimately, as long as your training uses some sort of model update where the update requires averaging, regardless of whether or not it is parallelizable internally on a specific layer basis, if you're thinking of you're parallelizing in terms of I'm doing the same operation on multiple machines in parallel, and at some point I need to combine the individual results, then the same thing would be applicable.
Got it. That makes sense. That makes sense. Definitely. Yeah. So one more question too. So you definitely went with the data parallel approach. Why did you not go with the model parallel approach?
Yeah, okay. So from the perspective of the model parallel approach, if you think of it, each one of these machines would end up computing. So imagine you have the first layer, right? And then once you finish the first layer, you have some values, which are then fed as inputs to the next layer.
Correct.
So in terms of what you can do between these layers, from the communication end, all you have to do is just send these values to the other machine, right? So there isn't any communication that needs to be collectively done in the middle. Whereas if what we're advocating for is anything that needs some communication that could be done within the network itself before it gets to the next node, why not do it in the switch? Like they have actually done other things where they'd use the switch. So if you think of maybe database applications, right? So imagine a case where you want to look up values in different tables and then combine them and send the result to the client. you can do the lookups in parallel and combine the values in the switch and then send them back to the client, right? Or in terms of applications where you have like key value stores, you could cache some of these values in the switches themselves and send them immediately. So, and this is like more of the scope of the work we're focusing on. It was what are these things where you could do computation within the network itself to make them faster. And if you think of model parallelism, there's really nothing substantial you could do within the network in between the two servers.
That makes sense. That makes sense. That's yeah, good answer. Yeah, thank you so much for joining us. There are no other questions. I really appreciate the time you've taken. Definitely.
Sure.
Yeah, thank you so much.
Sure.
All
Have
right.
a good day.
Take care.
Bye.
Bye bye.